Welcome to, I don't even remember what the number of it is now. What we are in the 30, no, we're on the 28th or 29th. Yes, that's right. It's my 29th. Okay, it's a pleasure to welcome Irina Risch, who's actually here in Montreal. She's appearing virtually because I think most of us, when we have a chance to appear virtually instead of in person, tend to take that, except for people that are very addicted to live audiences. She is professor of computer science and operations research at the Université de Montréal and at Mila. Her research is on machine learning, neural data analysis, and neuroscience-inspired AI, including scaling laws, emergent behaviors, all these topics that we've been discussing here, and foundation models in AI, continual learning, and transfer. With that, I'm pleased to pass it to Irina, who will share her transparencies. You want to share?
So I'm sharing, yeah, just a second. I'm sharing my, yeah. Okay. So.
No rush, it's okay.
Okay. Is it?
It's starting to display. That's it. It's there.
Okay. So let me just make sure that you see the full screen. And can you see the full screen now?
Yes, now we do. Thank you.
Okay, perfect. Okay, so let me just hide and that's everything. Okay, thank you so much for inviting me. And indeed, yeah, I mean, I wish I was there in person. It's just a few deadlines that piled up. It was kind of easier to do it online, but I hope that at least someday I can visit and chat with people in person. I also am looking forward to the panel discussion at the end of this talk. I know Blake also talked earlier this morning, and he also works on, he works much more than I do on the intersection of neuroscience and AI, while I kind of moved more from neuroscience side to the kind of core AI, and especially to that recent hot area of foundation models, and trying to understand what happens to them at scale, at least to some extent, and actually trying to build them while in academia. I'll talk about that later today because it's kind of a very interesting area with its own challenges when you actually not just try to study them, but we try to build them. But basically, without any longer introduction to like why we're doing that, I basically just want to take one high level look at the whole machine learning field and actually go back to even classical statistics. And if you think about the main question that usually was driving all those fields where learning from data was required, indeed, the good old century-old plus statistics. You try to learn from a few points, fit some curve, and you try to extrapolate or you try to generalize. So generalization is a kind of holy grail. You move to machine learning later on and you have more sophisticated multivariate curves to fit, but you still aim at the same goal. You want to generalize from what you've seen before to unseen examples. And then things get more and more sophisticated in terms of those multidimensional curves that you're fitting, and they can be modeled as networks like neural networks and so on. But the goal remains. So essentially, the whole kind of recent bunch of advances in the deep learning was always driven by the goal of generalizing further and further from what the model was kind of trained on. It included names such as out-of-distribution generalization, or transfer learning, domain adaptation, and so on and so forth, and continual learning with which is a topic I will talk about later. And there are many motivating examples which are quite amusing and interesting when people train models on images, for example, of animals trying to train the classifier of cows versus camels or something like that. And the model actually, instead of learning the properties of animal, latches on spuriously correlated features and learns to classify from typical background of those cows being on the grass field. And when you move out of distribution, show pictures of cows on the beach, the model is clueless. So other examples of this instability to distribution shifts or to out of distribution generalization was when people would design on purpose adversarial examples and add them to images just to test how the model would do. And people don't even notice the difference. The model is completely fooled by this type of adversarial attacks. So what I'm trying to say that the core challenge to all these fields is always how do you design systems, how you train systems that can generalize. And you can, in a sense, say that if you can generalize well, that's another definition of what understanding means. Like Blake was discussing this morning, there are various definitions. So how do we get to that point of generalization? And one thing is like, well, look, if you consider like humans who apparently can claim that they generalize well enough, and that's why we're talking about artificial general intelligence as like human intelligence. There was a whole history of kind of evolution when humans were, or even starting from single cells, organisms were kind of exposed to environments that were quite different, and they had to learn different kind of data distributions, different tasks. They had to keep accumulating this very different kind of principal components of the our kind of world or universe that we are living in. And perhaps if you accumulate enough of those and they are sufficiently diverse, then maybe you can grok the reality and you can at least adapt to the world you're living in. So it's kind of just a hypothetical thing, but maybe you can view the process of evolving natural general intelligence as a process of collecting the necessary principal components of the world and then finding a way to recombine them. And you can kind of make some strange saying that different areas of the brain to some extent specialize to run different tasks. So again, it's just a very high level speculation, but again, the goal is how do you build systems that can be highly generalizable to novel environments and tasks? That's essentially working definition of AGI. So AGI, or artificial general intelligence, though again, different people define it in different ways, but the practical working definition, you can say, just like OpenAI define it on their webpage, highly autonomous system that outperforms humans, or I would say just performs at least as well as on most economically valuable work, which essentially means it can do multitude of useful tasks, and it doesn't forget how it kind of what it learned before, and it can keep generalizing. So anyway, so not diving in too much into the definitions of AGI, let's now look at what's going on. As we all witnessing, there is this neural scaling revolution, right? And it kind of started this modern era of deep networks at extremely high scale. It pretty much started with the AlexNet moment of deep learning, when there's basically AlexNet deep network demonstrated that given a lot of data and a lot of compute to kind of build sufficiently large network to absorb this data, which in 2012 was kind of relatively large by current standards, it's not. The model can start outperforming all the state of art, like by more than 10% accuracy on ImageNet. And that was kind of the moment of revelation that just increasing data scale and increasing model scale and increasing compute without too sophisticated kind of ways of incorporating this generalization might actually let those models learn just like our evolved brains did to some extent. And since then, it's a log scale. We can see that the state-of-art models are kind of keep growing in terms of size and compute and data, essentially. So scaling revolution continues, and in the past few years, we all observed, basically with the advent of GPT-3 and kind of late spring, early summer 2020, there was this whole bunch of so-called foundation models that multiply kind of like rabbits or mushrooms after rain or whatever. But essentially, all these models were not particularly revolutionary in terms of their new architecture. They were just using already existing, but quite successful and simple but general transformer architecture. Just the scale itself apparently had a lot to do with a dramatic improvement in their performance. And then August 2021, there was a survey, like very nice and comprehensive survey paper coming out of Stanford that coined the term foundation models. It's essentially models that are pre-trained in, you can call it unsupervised or self-supervised way, without any particular goal of doing a particular task. Say it's not specific sentiment analysis program, or it's not a classifier of animals. It's just a model that learns probability distribution of language or images from humongous amount of data, just trying to model that, say, language well as predicting the next token, the next word, or the next kind of element of the language. That's all. It doesn't know what you're going to be using it for, but by the fact that it's scaled and has observed very diverse distribution of data, it now kind of knows how language is supposed to work. So when you ask it to do particular task later, you only need to show a few examples, a few shots for model to generalize. So in a sense, this holy grail of generalization was, if not achieved, I mean, there are still drawbacks of these models, but a humongous progress was made in that direction towards this artificial general kind of intelligent models. And I don't have to go through that, but we're all witnessing this, what many call Cambrian explosion of various foundation models, whether they are language models, vision language. There is also other type of modalities, including like audio, video, and more recently time series generically, and so on. So they seem to work well, mainly by advancing their capabilities due to scaling. And that's kind of classical plot from the this original GPT-3 paper, where they said, look, the GPT-3 is exact same architecture as GPT-2, and the only main difference is that few orders of magnitude increase in number of parameters and training data. Of course, there are underwater rocks in terms of like how do you train those large-scale models efficiently so they don't get stuck and so on, and they actually take advantage of their scale. There are engineering challenges and so on, but after checking like what really goes into improvement of performance, conclusion was that most important factor was scale. And that, of course, reminds some of us, I'm kind of big fan of that bitter lesson, short kind of, I wouldn't even say position paper, it's a blog by Rich Sutton. Actually, it was it was written way before the GPT-3 appeared, but it kind of captured what's going on in a sense at high level in the whole field. Basically, the bitter lesson says that, look, if you look at the progress of AI, then over the last 50, 60 years, the methods that basically stand the test of time and win eventually are not the most sophisticated, detailed, domain knowledge-based ones like some rule-based expert systems. Nobody uses really them before, right now. But the generic methods that can scale and leverage computation and leverage large amounts of data, they stand the test of time. And that's essentially whole history, right? You can look at the computer chess, people put together ontologies, heuristics and so on. And then essentially massive search defeated all those kind of nitty-gritty detailed type of systems. At some level, of course, as usual, there is quite a bit of engineering going into those, but the trend is the same thing. Computer Go, yeah, you have large-scale model that trained a lot, used self-play, and basically it's lends itself to scaling, and it's relatively simple. Many examples like language, speech, computer vision, people spend decades developing features, domain-specific features, and later on deep learning at scale simply learns those features automatically. And kind of all this like handcrafted stuff to large extent was not used anymore. And the lesson kind of keeps going on that the reason it's bitter is that in the short term, sometimes people are kind of tempted to spend time putting sophisticated methods, putting their exact knowledge in those models. But the question is always, will this method stand the test of time when more compute will become available and more data can be used to train the model? Are you investing your time into something that will be used 10 years from now? It's always a good question. And I think the conclusion of that bitter lesson I could resonate with that, look, maybe we shouldn't be trying to necessarily put into machines what we learned and the final result of that. Maybe we shouldn't be trying to put exact architecture, say that brain developed. But maybe what we should try to do is we should let them learn and evolve, and perhaps we should create the proper environments and kind of conditions for them to find good solutions. So they might actually find better solutions than we did. And that's a commonly used and very popular a few years ago meme about, well, GPUs go bitter. You just, instead of all this type of arguments of what you should be putting into your model and how to make it work, maybe you just need to consider scaling relatively simple but scalable approaches. For example, transformers were such things. So why scaling? So why do we really need to look into how our methods, whether it's architectures or particular optimization algorithms, or particular ways of selecting data points, whatever we do when we train models, why should we look at how they compare with each other, not at a particular kind of benchmark of fixed size or not at a particular size of the architectures? Why do we need to look at the trends? Because as usual with the trends, things may reverse. And what works best at, say, smaller scale in terms of data or model size may not anymore be the winner at larger scale. And you need to know that. And that was this classical example from the old paper, well, by now, by modern standard, few years ago is old, about vision transformers beating convolutional networks when there is really huge amounts of data available to them. At smaller scale, actually intuitively makes sense. Putting additional constraints or regularization or your inductive biases about how things work, like convolutional networks, somewhat inspired by vision, it does help when the data are relatively small. Just like in a sense, from Bayesian perspective, when you don't have much data, but you have a good prior, if it's good, then it really helps you do well. But imagine you have increasing like almost infinite amounts of data. Then first of all, this prior may be just kind of washed out by your data. And second, what if the prior was misleading or overly constraining? Then it will only prevent you from efficiently learning from this data. That's why maybe those simpler approaches without too much of constraints or inductive bias may scale better. So that's kind of something to consider. And that's why essentially those scaling laws or scaling trends can be used as investment tools. You want to know which method will stand the test of time, assuming that with time compute gets cheaper and more data will become available and models can be scaled. By the way, it's very interesting. It's not something recently invented in terms of this idea of looking at scaling laws. Back in 1994, actually, at the Core AI and Machine Learning Conference, New RIPS, they used to be called NIPS back then, there was a paper from famous people in the field, the classics, so basically Karina Cortes, Vladimir Vapnik, and others, and they made precisely same point I'm making now. They said, look, most of machine learning papers traditionally compare things at a particular data benchmark on something that's always fixed size. But what if the trends will reverse? You need to look at the trends. You need to look at the scaling laws. And that's kind of the history of the neural scaling laws from back 1994, where for the first time, to my knowledge, perhaps it was done before, but that's what we have found when working on neural scaling laws. People observed that actually quite simple functional form might describe how the neural network system scale. Back then, it was a simple, maybe few layer, fully connected neural net. And yet, with the amount of data increasing, it was in log-log scale, showing the straight line, which essentially means it's a power law kind of scaling of, in this case, log error with amount of data. So that was kind of, to the best of my knowledge, first time people showed the power law scaling neural networks. There was perhaps some additional work that went somewhat unnoticed, but there was a resurgence of interest in neural scaling in kind of late, basically 2017, and more recently, kind of culminating with a famous neural scaling laws paper by Jared Kaplan and co-authors. So people kept observing that power laws seem to hold at multiple orders of magnitude. They also may describe the scaling behavior, not just with respect to the data, but with respect to the model size. And as that seminal paper by Jared Kaplan and his colleagues showed, it holds also for the compute. So the plot in the bottom right corner essentially shows power laws for all three regimes of scaling. When you scale compute and allow your model, like try different sizes and different sizes of data and choose the best, then improvement in your test laws will be kind of following power law. Similarly, if you fix the data size and see how the performance changes while compute and model size are not bottlenecked, its power law with another exponent, and so on with also number of parameters, basically model size and data size. So this plot became quite famous and was probably, you have probably all seen it, because that was even on the t-shirts of some Mila students who would say that, okay, scale is all you need, AGI is coming. Anyway, the joke was around those plots. As I said, that's zoomed in picture of this main result from Jared Kaplan paper, which also concluded not only scaling with compute data and parameters follows power laws, but also they did extensive like ablation studies and tried different architectures, different modalities. And essentially the conclusion was that the most important factor that affects performance was scale. What are the advantages of knowing that? Well, there was a very practical one. Training GPT-3 or any large-scale foundation model requires lots of hyperparameter tuning and making many engineering decisions and choices. And you need to know which one will work better when you keep training and keep giving more data and allow the model to increase. So scaling laws truly work as investment tools, even for training large models. By the way, it's not just transformers specifically which shows this type of scaling. Even the simple multi-layer perceptrons actually scale. They may not be scaling as efficiently. They may not necessarily have like same exponent, but in principle, if you had infinite compute, you probably could just scale them to do the job. Now, changing gears a little bit, I was talking about the scaling laws and showing the test laws, basically how well you model your data, how well the model would actually predict the unseen data of that type. And that seems to be relatively relatively frequently modeled by those power laws. However, if you ask the question how the model will perform on what's called downstream task, like, you want to do it some specific language task, whether it's like, I don't know, sentiment analysis, filling in a word in a sentence, like they do on the tests, translating, or doing some specific task with specific metric, or trying to classify certain things and therefore its classification accuracy. When you're trying to see how those metrics on those downstream tasks perform, there are much more interesting behaviors, and especially so-called transitions or quote-unquote emergent behaviors that people were observing quite a lot. I mean, it is somewhat controversial, and there is lots of recent work like on the trying to understand what that means, why there are sharp transitions. Is it really emergence, or there is just a difference in how things behave for particular metrics? Yeah, there is lots of work on that, and it's quite exciting, but it gets more technical. The plots here basically show a few examples, starting from the one on the right, where you actually see, I think I have it. No, I don't have it. On the right, you see actually plots from the original GPT-3 paper from 2020, when they evaluated model on multiple different tasks. And here it was arithmetic. They wanted GPT-3 to learn arithmetic. And they realized that when they increase the model size up to certain size, models could not do it well. So accuracy was quite low on y-axis. And after certain model size, suddenly they would kind of grok or whatever transition, and the performance starts suddenly improving as if they kind of, I don't know, got enough capacity to do so. I don't want to claim we know exactly what's going on, and there are many hypotheses and papers and people studying like what is associated with this phenomena. But that was observed, that was interesting. Then after that, there was a paper called, well, basically groking paper with the plots that on the bottom middle. And that was essentially, I will talk about that a little bit in more detail. That was a plot where by accident, the authors from OpenAI left their program running and forgot to kill the process. And it didn't look like the model was learning. It was a particular arithmetic task model or something, I think. And suddenly, when they actually look at the result, they realize that after just running for a really long time, the model suddenly groked. And first, it improved the accuracy from almost 0 to practically 100 for training data. And then a long while after that, it did improve it. And that's what truly groking meant. It started generalizing to unseen examples. And that happened in relatively sharp kind of transition way, although it's actually in log scale. And then a more recent paper in 2022 evaluated multiple language tasks and observed that for many of them and for their particular metrics, there was indeed this kind of non-linear inflection point kind of sharp transition behavior. So it really made people explore this direction in more details. I'm not going to go over the whole literature, but it's very exciting code field. And I also was extremely personally excited about that because long time ago, way before deep networks, I used to work on constraint satisfaction problems. And the common part that with deep nets, there were also networks. And in networks, there are interesting, well, actual phase transitions happening under some circumstance, like in random graphs, we know there is actually theoretical results, Friedgut-Gallai theorem, saying that if you take empty graph and you start throwing randomly edges on top of that, and if you have any property that's monotonically, say, increasing its probability or decreasing. So it's monotonic in edge addition. Say connectivity, probability that graph is connected will only increase if you add an edge. There are many other properties. It doesn't matter what they are. The beauty of that theorem was any property monotonic and edge addition will experience phase transition if you keep changing on the x-axis the probability of having an edge between two nodes. So the denser the network, kind of say the higher probability that connectivity, the graph is connected. And at some point, the probability goes from practically 0 to 1. And in this plot, it's another property. So here it was a constraint satisfaction problem. And the critical parameter of that transition was constrainedness of the problem, like ratio between number of constraints or clauses. It was a 3 satisfiability case to number of variables. And that old 1991 paper showed empirically that when you increase this density of constraints, which can be viewed on the graph, on a random graph as adding edges, adding constraints, then the probability of the kind of problem being satisfiable, or like having a way to assign zeros and ones to all these binary variables so that satisfy all these clauses, it was going from practically 1 when there are many solutions to practically 0, problem is unsatisfiable. And the beauty was the transition was actually sharp, and just like in the proper phase transitions in physics and Ising model, it will become sharper when you scale that network, when you scale the model. So there is still kind of interesting direction to establish connections between what people observe in deep networks and transitions here, whether they can be called phase transitions, maybe, maybe not, depends. And understanding basically the theory of phase transitions from the physics, statistical physics model. It's a very exciting field. And another question could be, while we can try to understand why and what this happens, we also need a practical tool for capturing those scaling curves. Because remember, as I said, when you just look at the test laws, not at the downstream tasks, most of the time you have power laws, and that's simple. But when you start seeing some non-monotonic or with inflection points type of behaviors, you need more generic functional form. And last year we had this paper that appeared in ICLR, one of the key AI conferences as well, together with NeurIPS and ICML, led by a student of mine who is actually co-supervised with Blake, Ethan Caballero, who is really kind of diving deep into scaling and trying to figure out the scaling laws, and who actually introduced, I would say, the whole business of scaling to Mila, especially Mila Slack, from spring 2020, when nobody even kind of was considering that seriously. Anyway, so this work was essentially, I will not go into details and read all the formulas, and this is not a real curve that was fed to some data, it's just illustration of functional form. Basically, it turns out, which is in afterthought intuitive, that many of these more complex scaling phenomena can be described as a smooth combination of power law segments. So things behave like power law, and then they may smoothly kind of change the slope. How smoothly and when the slope change and so on and so forth, it all depends and can be fed to the data. Understanding that by looking at the training process is a holy grail, just like understanding physics constants from the first principles. Yeah, it's the same type of question, but I think it's exciting times when you can study those large scale models, pretty much like people used to study in statistical physics and in biology, large scale complex dynamical systems, because that's what they are. And the boundary between the other complex systems and the neural networks is blurring. The fact that we implemented them is less relevant now, because at some scale they start having their own life. Yeah, doesn't matter where they came from. So that functional form indeed was quite useful, as it was able to capture behaviors in different architectures, different problem settings for different metrics, not just like classification or loss or some alignment metrics, reinforcement learning, and so on. So it was indeed very generic and useful functional form. And under some circumstance, well, more work is required to actually make it work in more noisy situations, but in somewhat cleaner simulated cases, it could even predict transition way before it will happen. But again, if the stars would align. So this was a bit noiseless simulation, and you were close enough to transition, and transition was not too sharp. But that type of property of ultimately being able to predict the inflection points, the transitions, is extremely important, not just for better understanding those models, but from all the perspectives of AI safety. If there is some ability that's about to emerge, or the property that's about to change abruptly, if you can do anything about predicting when it's going to happen, that would be really nice. Anyway, so as I said, it was quite generic, and it covered pretty much the whole ground of various results that we've seen recently, being able not just to fit, but extrapolate the scaling performance. And to change gears a little bit, I'm just trying to see how much time I have.
You're okay.
Right. Yeah. Sorry, you were saying something?
You're okay for time.
Okay. Yeah. By the way, I mean, if there are any burning questions, feel free to ask me during the talk, because it's going to be lots of different topics. Yeah. Or you can ask me at the end. So basically, I'm continuing with the same kind of motivation that we want to predict how those models will behave. We know that they, depending on metric, may behave in easy power law, straight line, log plots, predictable way, or depending on what you want them to do and the metric, things may get a bit more kind of complex and unexpected. And we looked into this so-called closed box approach, like scaling laws, right? You just look at the performance and you try to fit something to it that will extrapolate. What if you actually looked into how the model learns, into training dynamics, into weights, activations, loss, and how all that evolves? Can you find any patterns that would predict that some transition is about to happen? There is also, as I said, it's now a very active area of work. It kind of overlaps with what people call mechanistic interpretability. So anything that looks inside the network training and looks at this learning dynamics and try to measure what might be predicting how performance or other behavioral metrics will change. So that was kind of another study. Again, it's all work in progress. There are some results, but there is so much more to do. And it's by now the whole kind of subfield, literally, that emerged in the past, I would say, 2 years. So the motivating example was this Groking paper, and we looked into that also with my colleague Guillaume Dumas from neuroscience at UDM, and student Pascal, a few others. But essentially, in that particular Groking paper that we try to understand, they looked at the simple problem of learning some binary operations. As I said, it could be an arithmetic or arithmetic model or something. And essentially, you have a table and you want your model to learn that operation. You split the table randomly into training and test, and you give the training data to the model. You can also do multiple epochs and keep going over this data as long as you wish until you grok, as we can see. And then you test it on this basically outcomes of the set aside kind of data set. So say 20% of this table was test data. And as the paper observed, indeed, we also were kind of observing the sharp transitions, where first the accuracy would stay 0, and then you kind of grok or understand or are able to do properly on basically with respect to the training data. And after a while, sometimes quite a while, there will be this second transition for what you really care about, which is a set aside unseen test data, or basically generalization. So we're studying like how it develops, like what are these different points and what are their properties, how that point T4 here, which is the most interesting, when you finally grokked, understood how to generalize what you learned, and how it depends on the amount of data. So clearly, yeah, so there is this dependence and so on. But what was more interesting is patterns, as I mentioned. If there are any patterns that can be early on predictive that there will be a transition happening, and it's quite empirical right now, requires better understanding why that's the case. It was quite interesting that in the runs where later on grokking will happen, we would observe on the right a lot of kind of high frequency oscillations in the loss, training, and test. While in the runs when we kind of never observe grokking, we didn't see such oscillation either. And intuition behind that actually came from various face-to-face situations where the quantity of interest start having really high variance just before transition happens. Also, basically, I remember the Guillaume Dumas kind of intuitions from neuroscience, basically like epilepsy, or from even climate studies, where high frequency oscillations may be a somewhat telltale sign of upcoming transitions. And apparently here it was interesting to see that a similar thing is happening with lots. So I'm kind of trying to go over multiple topics and switching gears again. So that was interesting stuff, but going back to the question of scaling and scaling laws. What is currently still an open area is incorporating more factors that may really help predict how those systems change at scale. Because the classical 3 parameters, like what happens is with the amount of compute, or the size of the model, or the data size, they, of course, are very, very rough proxies for what really matters. Because really, what matters is amount of information in the data, or diversity of the data, which is roughly measured by the size of the data if you assume that the data sampling is from domains such as internet. So by itself, the amount of data, of course, is not the factor. And one can come up with like adversarial examples saying, I'll give you multiple trillion tokens data set, but it's all copy of the same token. And no matter how much compute you throw on this data and how large the model is, it will not perform well. There is no information there. And similarly with the model, it's not, of course, just maybe the size, but it does matter what the capacity of the model is. But measuring those things is harder, and yet it would be interesting to nail down better how data properties and model properties approximate better this notion of capacity and information kind of complexity. There are more recent papers appearing that try to relate, say, complexity of the data through compressibility by gzip to scaling laws. But that's where we need more work on more fine-grained scaling laws that perhaps will condition on various important variables that we are not taking into account now. And one of those variables, by the way, is complexity of what you want this model to do later on. And essentially the cartoonish picture, say you want the model to do something what people call continual learning, or kind of trying to switch from classifying images of certain type to classifying images of other type, I don't know, different cars, different animals, and so on, and keep doing that. Depending on how challenging that downstream task is, if you build it upon pre-trained foundation model, you may need larger model, and it might have been kind of pre-trained on larger data. So obviously, If you just have very simple changes and kind of want the model to keep training without forgetting, it's not a very complex things. But if you want the system to be very versatile later on and, I don't know, switch from video game to video game, or you want to send your robot to Mars, and who knows how the environments will be changing there and what amount of versatility you will need, you may need to know how complexity of the task relates to problem size, the model size and the data. So if, say, I'm a company and the customer comes and says, I have this stuff I want to use your model for, it will give me idea just like how much compute I need to invest and how large of a model I need to build for them and kind of what data would be sufficient. So none of that is systematically studied yet in the field of neural scaling laws. So, of course, there is this big open-ended question, just like in the original quote from Rich Sutton that I mentioned, perhaps we should not necessarily incorporate in the models the final result of our knowledge, but perhaps we need to incorporate how things develop naturally, so the constraints on the kind of evolution. And here, it would be really interesting to understand how in the nature different networks evolve. Not just neuroscience, biology, and so on, because it's all about basically network evolution in any natural system. It doesn't necessarily have to be neural, but it's all about how the growth of some multicellular organism with changes in interactions across them, how does it all lead to increased complexity? And what can we learn from that so we can maybe also grow our networks in smarter way. And the classical example is that, of course, size is not all that matters, because you have elephants and whales and they have very large brains, larger than humans, and yet their ability to generalize and perform out of distribution is apparently not quite comparable to ours. So it's not just the size of the network, but apparently architecture and perhaps other things. So that kind of remains to be explored. Not talking about the fact that, of course, our artificial neural networks are still what's called the generation 2 neural nets, as they were kind of called when the work on spiking neurons started and so on by Wolfgang Maass and others. The claim is that brains, unlike artificial neural networks, are never ceasing to be active complex dynamical systems. Even if you don't show them any image to classify, even when you're sleeping, the activity is always there. So communication keeps going on, right? So where is memory? Where is the ability to adapt? Perhaps, there is lots of studies, of course, in neuroscience, how changes in the brain kind of dynamical properties, frequencies and so on, how they actually relate to different mental states, to disorders and so on. So maybe all that information is kept in the properties of dynamics. And that's not quite reflected in the today's kind of artificial neural networks. It's an open question whether we do need to follow that route, or maybe even without that dynamics, just scaling the traditional artificial neural networks may get us to high level of generalizable intelligence. It's an open question. So yeah, but that was just to demonstrate that on the left you have zebrafish brain. It's an old YouTube video. On the right you have like fMRI. You basically see that the activity never ceases to exist, even without kind of clear inputs or clear tasks. So it is kind of inherent there. Okay, so at high level, yes, that's a kind of easier said than done ultimate goal that people were talking about, I think, since the beginning of the computational neuroscience and AI, and especially deep networks. ideally, you would like to understand what's inherently like necessary for intelligence, whether it's artificial or it's natural. Like what is invariant kind of laws that underlie both, assuming both are some kind of networks. I mean, the question is still out there, as we all know, and in various ways, people, including us, trying to get to this hopefully invariant set of regularities and laws. Changing gears a little bit, and I'm kind of probably getting closer to the end of my talk, talking about what else can be done differently and how perhaps modern neural networks could become even more powerful. There are alternative approaches to kind of developing intelligence, which are not necessarily based on autoregressive model training of language, for example, or having some optimization problem that trains the network with respect to success on particular predictive tasks. So there was this interesting work coming from basically Antonio Damasio and collaborator. He is a famous neuroscientist who primarily, of course, worked for many, many years on the link between mind and body and essentially understanding like feelings and emotions as signals from your body, just like your senses are signals from external world. And therefore, basically not necessarily separating, that's why Descartes' error book, not separating kind of mental functioning from body, because it's just one complex dynamical system. And there are some recent papers like this one I quoted here, which suggest that perhaps we should create environments where there's artificial networks or agents supposed to survive, and there is a notion of them being hurt or even dying, and perhaps intelligence can emerge if their primary goal will be just to maintain homeostasis with their environment and just kind of continue to be. You don't need any specific objective except for the objective of remaining alive. Perhaps, as they argue in that paper, that could be an alternative way to training and developing intelligent systems. Anyway, so it's very kind of interesting line of work. Of course, it's very much unknown in the modern kind of AI and large foundation model literature, but it's like various thoughts about what else can give modern AI extra edge over what it has right now, and what can possibly be a faster or maybe more efficient way towards general intelligence. In the last, I don't know again how much time I should leave for discussion, but yeah, you tell me when you think I'm...
No one wants you to stop.
Okay, okay, because be careful saying that. I can talk for a very long time, as my students know. Right. Okay, so...
Right, but I have a question for you. Why do you
yes.
think control theory is so isolated from neural networks?
I think it's just historical reasons of perhaps, I don't know, it's not completely isolated, by the way. So reinforcement learning often connects with the control theory, and time to time, by the way, the recent hype in the AI about state space models kind of revisits it again. So there was this paper from Stanford a few years ago, like bringing back state space models to improve some shortcomings of these transformers in terms of, say, attending to the past, potential like infinite past, very long sequences being more efficient, like linear time instead of quadratic time of transformer attention. So there are connections being made. It's just the question is like why they're not more mainstream but they maybe should be. Yeah, I think it really depends on it's an interesting dynamics of thought within the field. And it's also like it's just like with any social network studies, like what gets popular, what goes viral as a research topic, and why some other research topic doesn't go viral. And that's an interesting question. So maybe there is a bit of a layer of complexity for people to kind of understand control theory if they are not trained as engineers and they're trained as computer scientists. It was not on their curriculum, so they kind of just don't know enough about that. So that's why it's always nice to have students from the engineering department, not necessarily just computer science, because they know signal processing and control theory. So it might be basically those reasons. So people tend to stick to what they were exposed to or what's already popular. And that's preferential attachment of Watson-Strogat's model of the research network. I don't know.
Wouldn't you predict with your hope that there might be some general principles of phase transitions that are common with physics, that this would converge with control theory, which is also in its way realistic in ways that neural nets are sometimes not so realistic, at least not so neural realistic.
Well, perhaps if there is, okay, so maybe with enough effort of trying to sync up the fields, at some point, I don't know how much of that effort will be required, you could reach certain threshold after which it will just take off on its own. So if you manage to make control theory, well, as I said, state space models kind of already became very popular, and there was this resurgence of them, although, I mean, it still remains to be seen to what extent they actually going to replace transformers. Initially, that was kind of claimed, but I don't think it necessarily going to happen, and hybrids probably will be, as usual, hybrids survive best. But I guess maybe injecting more control theory into AI work can reach certain threshold where just the research network dynamics will start working on its own, and that becomes popular and cool. And then there will be more research on that, and then the gets richer, dynamics will work. Again, I'm simply like brain dumping the first thing that comes to my mind right now, but I think it may require some initial extra effort to make this sync up happen. And of course, just like basically people pay attention to things that can demonstrate some impressive results. Deep networks were not really taken seriously for many years until 2012, that AlexNet moment. I do remember being at NeurIPS and Geoff Hinton trying to run workshop on deep networks, back then called deep belief networks. Workshop was rejected. People were laughing. People didn't want to even look at this stuff. They said, well, neural nets do not work. I mean, too inefficient. Like we all know that. Let's do, I mean, convex optimization was a hype or something else. Of course, Geoff organized that workshop anyway, and I remember it was almost like a secret society meeting on a day when everybody was moving from Vancouver to Whistler. That's usually kind of during NeurIPS, you go between conference to workshops. So the workshop or symposium did happen, and I have some very funny quotes and videos from that one, but it's a bit tangential. I can share later if you're interested. Bottom line, it was not mainstream. There was a relatively small group of people who believed in that, and it took basically AlexNet, ImageNet, showing that, okay, guys, here is a 10% improvement over all of your state of art. So people started paying attention. And that's why it was called the AlexNet moment of deep learning. So after that, people started taking it seriously. I think with whatever topic, if you manage to show that using that approach in some way can actually lead to significant improvement, significant difference. It doesn't have to be just improvement in accuracy. Maybe it can solve something that the current models are struggling with. I think it may create such a AlexNet moment for that topic X that you are thinking about.
Do you have the Q&A streaming for you? Can you look at it?
I don't know. Do I?
Yeah, well, yes, you should go down to the bottom of the Zoom screen, do the
I
Q&A.
didn't see anything because I was only looking at my slides and it was full screen.
Okay.
But right, yeah, there are questions here.
In fact, Claudius Gross's one was addressing what you were just saying now. You may want to read it out and
Okay, so let me do that. Plus, as I understand, we have time until 3, right?
yes.
Okay, and basically the rest of my talk is essentially just showing a few examples of what we are actually able to build and like how to do it in practice, because there is a huge gap, as we all know, between academia and industry in terms of compute. That's why, yeah, I kind of wanted to talk about that, about like, well, how do you actually do that? Because you do need some compute for that. But back to the ideas. Okay, so thanks, Claudius. Okay, the big step forward with transformers and attention was introduction of information routing, supplementing classical information processing of deep networks. Well, yeah, scaling is important, but not everything. Yeah, I know. I mean, it's never everything, because it's important and it can basically the major thing that makes things work, but you still need to make it work, right? So even with GPT-3, just having like close to infinite compute by at least academia standards at OpenAI doesn't mean you need to know how to scale those models. So in terms of attention, yes. So it was not just scale, but also the ability of transformers to model like long-range dependencies and be able to tease out using attention mechanism what's most relevant to like current situation. Sometimes there are long-range dependencies, and that's very important. I mean, basically, it's almost one of the properties of a smart system, the ability to remember something far kind of in the past, even like relatively to your kind of, relatively to your context window and so on. So that's why improving that is kind of where everybody is trying to propose something better. And the state space models like Mamba and so on, they say, well, hey, we can have a better treatment of very long range dependencies, and that will be computationally more efficient than your attention. On transformer side, people try to improve attention efficiency, and just like the context links kept growing in the past several years, right? So every time there is a new paper increasing that. But yeah, so the ability to kind of keep in mind of the model that there may be, something back in time, and having a flexible way of kind of incorporating that into prediction. Yeah, it's not just scale. Then question was about
David Austinson this.
Yes, a new Reeves paper by oh yeah, I knew this question is coming. Rylan Schaffer, yes. Right. So whenever people these days hear emergent, they probably have seen all kind of headlines based on that new Reeves paper. Rylan actually presented his work in our scaling workshop last summer. Also, we keep running the scaling workshops at pretty much all the large conferences, or sometimes just in Tremblant. That's how it started. Yeah. So his point is essentially that what you see as threshold, I mean, the kind of emergent behavior or sharp transition may be a property of particular metric, for example, discontinuous metrics, or like accuracy, for example. So the paper was titled whether the emergent abilities are a mirage. And I think by now consensus is no, they are not. In many cases, as he pointed out, for those tasks that the emergent abilities kind of in language models paper, indeed, if you look at other metrics and the loss, it's smooth, it's not emergent. But say in grokking, even loss metric can have still those kind of sharp changes. So it basically happens even in those metrics. another kind of aspect is you might be actually interested in the metrics that you're using, and you need to know what will happen to them. So you do want to know how their scaling looks like. And yeah, I mean, it was interesting to put things in perspective and bring the attention to looking into how scaling changes across metrics. Actually, Ryland just put on arXiv another paper recently, like about a week ago or so. And it's also trying to tackle this question of like why predicting scaling behaviors on these downstream tasks is such a different story from the kind of usual test laws, and why it might be so difficult. So it kind of along the lines of that paper. And hopefully he or his co-authors can present it at our upcoming scaling workshop that's co-located with ICML in Vienna on July 22nd. It's not actually ICML workshop, we just co-locate. So basically, the answer is, as usual, it's complicated. No, they are not a mirage, but yes, it does depend on the metric. Suggestions for current PhD students in AI. Wow, that's a broad topic. Suggestions of Parvez? Yeah, so suggestions of what kind? Research topic? Or kind of like basically like among all these directions, like what to jump on? Right. Or actually, I don't know if the people who are asking the question can unmute themselves and
they can't in general. Sometimes they can be upgraded. A few people have been upgraded.
I see. I see.
If you see names in the attendees that you want upgraded, I can do it for you.
Yeah. So I'm just trying to. It's very general question about suggestions. I assume the question like which direction and which topic, and I mean, definitely it's important, although I don't have a good answer to how on earth can you possibly stay on top of all recent developments, and probably no, you can't. Although I would suggest at least kind of, I don't know, I'm subscribing sometimes to some blog posts and so on, where people actually do this job for you and try to come up at least with highlights and gist of like what's the recent most important thing. So at least trying to stay on top of what's actually relevant and hot now. I know it's always trade-off because there are some things that are hot, but they may not survive the test of time. So ideally, like everyone, whether it's PhD student or the senior researcher, nobody wants to be better lessoned. But predicting is hard, especially about future, right? So how do you know? So I don't know. I would definitely suggest to at least try to stay on top of recent developments. And for that purpose, like crowdsourcing might be good. I'm almost about to suggest people to spend some time on Twitter, because that's where the most recent hot papers and topics are being discussed. But it is, of course, a can of worms. So you need to learn how to use Twitter for your advantage without all the crazy things that can happen to you there if you kind of get derailed and so on and so forth. So it's like a modern skill how to filter out useful information without getting too involved into useless, harmful waste of time. But
use an LLM as a front end to Twitter. But the priorities here are that with hands raised, they get priority over the list. So Steve Hansen and Rob Goldstone.
Okay, because I do see a bunch of questions in the list and it goes on. Okay. So some were comments, not really questions. And then, yeah, so it's just comments about which paper I was.
If you look at the screen, you'll see that there are two people, Steve and Rob, who are ready to ask you a question, and they have priority over the list.
Okay.
Go ahead, Steve, and then.
Okay.
Hi, Irina. It's Steve Hansen from NIPS, now called NeurIPS. You may remember me from the brain imaging and neural network groups that you took over, actually, at some point. So this is really fascinating stuff that I'm less aware of, although I know about power scaling laws and criticality and dynamics and stuff like that. So I'm sort of curious your interpretation of these scaling laws. And of course, you're seeing critical phenomena right in learning. So it looks like the dynamics are something's changing. So let's imagine that there's some graph structures in the attention heads and they're somehow, congealing into something important. We don't know what, but then we see this giant sharp learning curve that something important has been acquired. And is any of your research focused on what's been acquired? Let's say we're doing like arithmetic or some simple language system, but the power scaling laws, getting back to that, which worries me in all this story. If we go from GPT-1 to GPT-5, which is probably appearing any minute, unless Sam Altman hides it somewhere. But let's say so we're going from hundreds of millions to 1 trillion connections. Now, the human brain has probably 100 trillion connections, roughly. And yet it obviously has more structure than a feed-forward net and a bunch of autoregressive, and that structure, like the fMRI was showing, is showing a whole bunch of recruitment simultaneously bilaterally across the brain that produces, again, some unknown network computation. And so it seems like we're in the same boat here in terms of the neuroscience and looking at these LLMs. So the power scaling law is interesting to me because I don't understand what it implies about the underlying dynamics and the criticality. Could you explain that a little bit?
Yeah, I mean, okay, so it's a good open question. Although people recently, there were various papers. There was last NeurIPS paper from MIT, from Mark's group, Eric, anyway, so there was about like quanta, like acquiring, basically they're trying to put together a theory of how you get power laws and how this process kind of can be modeled by acquiring some basic skills or quanta of the, I don't know, whatever kind of action elements or whatever. So basically whatever skills kind of are there. There is a more recent paper actually that tries to also put together some unifying theory, as they claim. I still need to read it more carefully. That's also based on this supposedly process of acquiring those kind of atomic elements, and then eventually that would lead to emergent properties. There are various flavors of that, which reminds me that I put that picture about originally in continual learning setting. I was saying that like if people want to achieve the generalist agent, one can view it by analogy with learning principal components in the most trivial case of linear autoencoder or SVD, and you keep getting samples of data from some huge n-dimensional space, and you keep learning new kind of orthogonal components, and the more you learn, the more kind of part of the space you can cover with those components. So let's assume that the world we live in is, if not finite dimensional, at least well approximated by some finite, maybe humongous number of such components. Again, I'm still living in that linear space, so it's still an analogy, right? And then if after some point you get pretty much all these necessary components, since it's finite number, you kind of grok it, because whatever later on comes your way, you kind of recombine them, in that case linearly, right? But in reality, not, and you can pretty much approximate well any data that comes from that space. So this is analogy with pretty much acquiring a set of principal components of the world or universe around you, assuming that it's such that it's possible. And I think the intuition could be, it probably is like that. Otherwise, we wouldn't be able to survive with a finite network in the brain. So the fact that we're able to survive kind of hints at some approximability of the universe with finite set of principal components. I might be wrong. It's just purely a hypothesis. And then, of course, you can say, but it's not linear vectors, our data. And say we want to do supervised classification. We want to learn functions. So I keep learning functions as I keep going, say, continually from, I don't know, CIFAR 100 to MNIST to something else, and then further and further away. I keep learning functions. So if it's a functional space, can I approximate that functional space with finite set of functional components? And how do I recombine them? Again, it's all analogies, but say by analogy with a basic SVD, maybe if that's the case and it's possible to do, then you have what's called the compositional generalization. If you get the components and everything is more or less approximable if they recombine properly, you grokked it. So that's why a joke in my group is like, I know where we achieve AGI. You get all the main principal components, that's when you achieve AGI.
Okay, Rob has been waiting patiently for his turn.
Okay.
Rob,
sorry.
welcome back to Montreal.
Thanks. Yeah, it's great to be here, and that was a great talk, Irina. It was really super informative. So you're describing laws of scaling in which models that have less inductive bias perform better compared to the ones that have more inductive bias as the data size increases. And I guess I'm curious about how more and less biased models do as a function of a different kind of x-axis, not the data size, but the degree of dissimilarity between the training and the test results. So I might think that a model needs to incorporate more inductive bias as the difference between the train and the test sets increase, because models that have less inductive bias might be expected to overfit the data and not do well. So I guess I'm assuming that there's sort of a continuum of how different the test set is from the training set. And it seems like maybe inductive bias is good because you need a model basically in order to handle something totally different. I guess I'm thinking like if you're trying to predict the economy and then something totally different comes in, like Bitcoin, right? Which hasn't been in the training set before. And you want a system to do well predicting the economy with Bitcoin in the future.
Well, actually, if you look at what foundation model do, the whole claim to fame is they do generalize out of distribution to totally unseen and untrained on tasks few short, hypothetically due to the fact that although they don't have inductive bias per se, they were exposed to such a large and diverse amount of data, and they are large enough, and say you train them properly, they can actually absorb that information. So they kind of maybe got these components that are important. So even though your data are out of distribution, you can still recombine the information and still work well with this very out of distribution data by maybe just showing model a few examples. When the whole actually claim to fame was that foundation models seem to, well, if not solve, but considerably alleviate the out of distribution generalization problem. And if you look like the clip back in 2021 was indeed like surprising that I worked on out of distribution like many people. It was so exciting. We all tried to put particular algorithms like invariant risk minimization. We're trying to apply that, invariant learning consistency, all these things about how do you make model infer stable invariant features. So just the whole model is stable invariant even to distribution shifts. And then you say, well, you just scale it and expose it to lots and lots of diverse data, and then it just a few short generalizes. So, and the question was indeed like, what to do? So basically the inductive bias was apparently playing less and less overall because data were allowed to talk. So, and I guess that's why I was bringing this Bayesian analogy that like in, how to say, in asymptotically. So basically like if you have some very generic model that will be exposed to well-sampled data, that's maybe it's all you need, because you may incorporate inductive bias, but it will be either washed out, or imagine it's not quite right bias. It will take even more data to wash it out then. So the question is like, where do you stop and what is the right amount of the inductive bias? Because pretty much anything is inductive bias. Even the transformer architecture with attention is inductive bias. The fact that we're running SGD and not something else is kind of inductive bias. I mean, it's like impossible not to have some way of doing things which can be called inductive bias. I don't know, but it just seems that if there is, I mean, the example of convolutional networks and some other examples was that maybe, you should have inductive bias in right amounts so that it will not over-constrain the training. So whatever you do, it should not slow down kind of the training from data. It should let the data speak. And the model should be able to hear that and incorporate that. So in this sense, like sometimes overly complicated inductive bias might not be good for you. But what overly complicated versus just right is, depends.
Okay, now we really are running out of time. I do want to draw Chaim Dubrovsky to the discussion. Is there anything in your, he spoke about language change just before you came. Is there anything in your dynamics of language change that looks like grokking?
Okay, so actually there were a few slides, although it may be tangential. When you talk about language change, you're talking, for example, if you want to train multilingual model, for example, something like that?
This is actually addressed, Chaim will say it in his own words. Go ahead.
Hi. I can live with what Irina said about cross-lingual perspectives, because from a certain type of perspective in linguistics, you can say, as I try to mention, that diachronic or historical change is not very far from language variation. Language variation is a bit related to language transfer, task transfer in NLP and machine learning. So Irina, if you have some slides on that, that would be really interesting for me to see.
A bit maybe tangentially related, but basically I completely skipped whole part where I was talking about what we were building, and essentially like say it within 1 minute and get to the multilingual models. Right, I mean, we had to find compute. We applied, and by the way, it's open to anyone. So large scale kind of compute grants you can kind of apply for at various supercomputers like Frontier and Summit. That's basically what we used for training some of the models in the past 2 years, and large collaboration around that. So we had various projects, and it's like an incomplete list, but one of them was with language models, training from scratch and continual training. And when we trained continually, we indeed also trained some multilingual models, like we were switching from English to German, we're switching from English to Hindi, and we were training continually. To make long story short, is we were trying to use some simple considerations to make sure that when you switch to new language, say, or new data in general, you do not forget what you learned before while you're still able to adapt. So classical stability plasticity kind of dilemma, how to do it well at scale. So that was like last year we trained actually like 4 billion language models, some continually, some did some comparison, had the recent paper in the journal TMLR. So details are there. Then this Hindi model was also like, so basically if you're careful, you can absorb kind of continually new language without forgetting the previous one. So basically kind of this type of things that you can do, although continual learning is not yet mainstream in the, say, this all large scale open source modeling, and it probably should be. So we're trying to basically advocate for how do you Yes, I mean, there is more information online. Don't have time to go through that, but basically advocating how you should be going about training, especially open source, like medium-sized models, like what people can afford, like 10 billion, 20 billion, and so on, given the, say, government compute, although in this case it was US government Frontier and Summit, the continual training with proper tricks about replay, learning rate schedules, and so on should allow you to keep balance between adaptation and forgetting, so you can, say, keep learning, like, say, new languages and so on. Instead of doing this traditional training from all different type of data sets mixed together, it's not very practical because data will keep copying. You want the model to be extended to, say, new language and so on. You will need this continual learning. So maybe the elements of that would be related to your kind of question about how to go multilingual. But yeah, so I think I'm kind of really running out of time, so I don't have time. By the way, about this continual learning, it's possible to make your model train continually. At least, again, it's initial results. Much more work needs to be done. But you can pretty much keep the performance of the standard large-scale foundation model you would have trained if you mixed all data together. You can kind of reach that while doing things much more practical way sequentially. So that was our recent TMLR paper conclusion. And that directly applies to switching, say, from English to German here or to Hindi.
Wonderful. Hindi is a special problem for Chaim, but I have to cut it off.
You have to cut it. I don't have time to talk about alignment and viewing Derek Parfit on what matters as application of invariant risk minimization.
Irina,
yeah, I can explain offline why I think that's the case.
You don't have to explain offline. You will have another chance in the panel. Many of the same people will appear.
Okay.
Or take a break, relax, and wonderful talk.
Thank you, and looking forward to the panel. Okay.